Alright, so welcome back to Particle Physics and the Standard Model. This is lecture 49, right? And last time we delved a little bit more into particle collisions, and in particular we took 2 to 2 collisions because that's what we see most of the time in real life situations. We talked about space-like scattering and time-like scattering as defined by the momentum transfer square, the sign of the momentum transfer square, and we asked if we want to create new particles in the final state, how much energy should we put in, right? So we worked out the total energy in the initial state, rather we worked out the invariant mass of the initial state, yes, and we wanted that to be larger than the invariant mass of the final state. So stands to reason, right? And two popular configurations for doing this is the fixed target experiment and the head-on collision experiment. Okay, so fixed target is just what it sounds like. The target is stationary and then you throw a projectile on it, and we worked out what the invariant mass square of that configuration is in terms of the mass of the target and the energy of the projectile, right? In particular in the case where the mass is negligible compared to the momentum of the beam. That was 2m times Ea, where Ea is the beam energy. And when we work this out for head-on collisions, right, where we took the lab frame to be the center of momentum frame, right, we arranged the lab frame such that it is a center of momentum frame also. In that case we saw that in the initial state, you have the total energy that you pump in is actually 2 times the energy of each beam, assuming each beam has the same energy, right? So that's what we got to last time, and that showed us this scaling between the total center of momentum energy and the total energy in each beam. For a head-on collision, the scaling was linear, and for a fixed target, the scaling goes as a square root, okay, with the mass of the target compensating for the dimensions. And that meant if you want to discover new particles, new heavy particles, then you are better off using the head-on collision method, okay, like the LHC and so on, okay, because just like that you can pump in a lot of energy in the center of momentum frame and create the particles that you want. So this came to be known as the energy frontier of building colliders and looking for new physics. The other one, where you just have a fixed target, you cannot actually put in a lot of energy in the center of momentum frame. Nevertheless, it's a cheap way to set up an experiment, and so what you can have instead is many more collisions, many more events to work with. So that came to be known as the intensity frontier. Okay, both are equally important. Okay, one is to discover heavy species in the mass frontier, the other is to discover probably lighter species that have escaped our attention. Okay, not just discover but also make a lot of precision measurements. Okay, so let's continue on that theme, and I'm just going to give some examples of these two frontiers before we move on to other things. So at the energy frontier is where we have most famously now the Large Hadron Collider. So what do they collide? At the moment they are colliding protons on protons at a center of mass energy of 13 TeV. Okay, might as well write in my notation it's ECM, right? And then before this there was the Tevatron in Fermilab USA. The LHC is in CERN. Tevatron was in Fermilab USA. They collided protons on antiprotons, okay, at an energy of 2 TeV. They collided it at many different energies. The maximum energy that they went to was 2 TeV. Okay, And before that, again at CERN, there was a LEP, um, lepton electron collider, and they crashed basically positrons and electrons, again in the center of momentum frame. Well, again the lab frame was made the center of momentum frame. Okay, and the maximum energy they went to was 209 GeV. Okay, 209 GeV has an historic implication because the Higgs is at 125 GeV, right? The Higgs mass is at 125 GeV, and with this method you have to create two Higgses. Most of the time you are trying to create two Higgs Higgs bosons in the final state. They just didn't have enough energy at LEP. This is the reason that LEP did not discover Higgs, although they wanted to. It turned out to be LHC that discovered the Higgs, and around the same time Tevatron also saw the Higgs because they had the energy to do it. Okay. Okay. Now what about the intensity frontier? Here are some examples. I recommend you go look these up, on Google, Wikipedia and so on, so that you get a sense for these experiments. You can see how the detectors are built, what strategies people used, okay, and things like that. So one is Na62, I believe this is also at CERN, and they had a proton beam. Okay, on target, and their main aim was to from this get K plus mesons. So they got a K beam with which they measured CP violation parameters, looked for exotic particles, etc., etc. Okay. Another one that's coming up now is the DUNE experiment using the DUNE collider. Again, it's protons on target, and the aim here is to get a neutrino beam and do all sorts of things with it, including measure neutrino oscillation parameters. Okay, so DUNE is coming up soon in Fermilab. American physics is all focused towards that right now. Okay. All right, particle physics at least. Now, to again illustrate using some real examples, the difference between the center of the head-on collision configuration and the fixed target configuration. At the Tevatron, the energy of each beam was TeV, right? And so you got a center of momentum energy of 2 TeV, right? But the same, if I were to get 2 TeV, okay, let's call this, this has another notation, I'll just call this ECM. Okay, so ECM is twice of this, which was 2 TeV, right? Now, suppose I wanted 2 TeV center of momentum energy at a fixed target experiment. Okay, then what should I be doing? What is the energy that I need in my beam? So let's look at this formula. This tells me that the energy of the beam should be the center of momentum energy squared over 2 times. In this case, you are hitting protons, right? The fixed target is also protons most of the time, right? So that's what I require, and what is that? If I want 2 TeV, this becomes 2 TeV squared over 2 times GeV, right? And what does that give me? That's basically 2000 TeV. So you can see the difficulty of producing new particles with a fixed target experiment. Better to just create 2 beams of the same energy and crash them against each other collinearly, as collinearly as possible, right? So it's today it's impossible to create a beam with energy 2000 TeV. So Okay, very good. So with that, let us now move on to one of the most important concepts in colliders, but not just in colliders, in particle physics, and I would even argue that in all of physics. Okay? A concept that seems to confuse everybody in the beginning, but once you get a hang of it, it makes complete sense to use this quantity, the cross section. Okay? In particle physics, especially in nuclear physics also, you'll keep hearing what is the cross section for this, cross section for that. Okay? And there is a related concept which is not that hard to understand. We've been seeing this since high school, which is the decay rate. But we'll see how these are related. The decay rate is a subset of the concept of cross section in a sense. Okay? So, what do we mean by cross section? Okay? So, I'm going to give you a heuristic picture first, and then we'll build it up to deriving a proper expression for cross section in a most generic case. Okay? I'm going to say, let's take a box filled with balloons. Okay? Okay, my drawing skills are not that great. So I have a bunch of balloons. Okay? And I determine the number density of the balloons. I'm going to call it n balloon. So let me just write it, number density. Right? So I can fix the size of the box. I can fix how many balloons I put in. If I can fix even one of these, then I can decide what the number density of the balloons is. Okay? Now, let's say I am going to shoot this box. Sorry, I'm going to shoot at this box. Okay, again, don't mind my drawing skills. That's a gun. And I'm going to shoot it with a bullet. All right. Would you now agree that the mean free path of the bullet as it hits the balloon, so it's now going to keep hitting the balloons as it goes along, right? Nothing is slowing down the bullet. The balloons are not going to slow down the bullet. It flies through and hits the balloons along the way, right? The mean free path is literally what it is. I mean, what it says is the average distance between two hits, right? You would agree that the mean free path should be proportional or inversely proportional to the number density of the balloons. Correct? Right? So the more I squish the balloons, the smaller the mean free path is going to be. The more frequent are going to be the hits. Yes? So I bring this up because if you remember this example, this is enough to actually build up the rest of the concept of cross section for any situation. Why? Because the dimensions are not working out right now, right? To get the dimensions right, I need to introduce something down here with units of area. Yes? Because this has units of length on the left hand side. Number density has units of 1 over length cubed. So 1 over number density has length cubed in the numerator. So I have to introduce something with the units of area in the denominator, right? Now that something is nothing but the cross section. Okay, and in this particular case, it is nothing but the scattering cross section. Okay, good. So let's rewrite this slightly. If I want to define the cross section in this system, I would say that the cross section is, so I'm now bringing down the number density. So I'm just exchanging the left hand side and right hand side, numerator and denominator. So I still have the number density of the balloon downstairs. The mean free path is nothing but what? It's nothing but the total number of hits as the bullet traverses the box, right, divided by the length of the box. So let's call this length L. That's a mean free path after all, right? So what does that mean? If I basically, if I want to measure the cross section for this system, I shoot and then I just record the number of bursts that I hear. I know the number density of the balloon, I know the length of the box, I can calculate what the cross section is. Okay, so you simply set up an experiment to measure the cross section. Okay, suppose I don't know the length of the box. Okay, suppose it's some very, very long box and I don't know the length, but if I knew the speed of the bullet and the time it took to, if I could measure, if I actually have a clock to measure how long it took for the bullet to enter and exit, between entry and exit, that also tells me how to measure the cross section, right? So in all this, what I'm implying is that the cross section is intrinsic. This is not the thermodynamic intrinsic. Okay, I'm using this as an English term here. Okay, it is intrinsic to the scatterers. That is, this was not in your hands actually. This depended completely on the properties of the balloon and the bullet. If the bullet had been really large, maybe the cross section would have been larger. Similarly, if the balloon had been large, the cross section would have been larger, right? And if it was small, if either was small, then the cross section would be smaller, right? So that was intrinsic. This was not in your hands. You are finding out some intrinsic property of interaction between the bullet and the balloon. Okay, so the cross section is not in your hands. That is the point here. Whereas these things, right, the number density of the balloon, the speed of the bullet, the time, and all these other things, these are, maybe I should have marked it in a different color. So things like these, the length of the box, these are things that you determine, right? So these are all basically extrinsic. Again, not the thermodynamics extrinsic. All I mean is this is in your hands basically. So you can set up things in your experiment in order to measure something that nature has given you. Okay, that really is the point here, and the measurement that you make here is the number of hits, right? You set up everything and then you measure this. That gives you what the intrinsic cross section is. Okay, so that's the introduction to cross section. Now let us generalize this a little further, okay, and see yet another slightly different version of what the cross section is. All right, I'm going to say, suppose, okay, you now forget about the balloons. Okay, suppose you had one rigid target, let's say some rock or something like that. Okay, and instead of one bullet, you have a beam of bullets. Okay, this is like some submachine gun that just keeps spraying bullets on some rock or some very hard rubber ball. Okay, then I'm gonna simply generalize this equation, or rather extend that equation to a different notion. Instead of hits, let's call it the number of scatters. Okay, and down here, instead of number density of balloons, now I'm going to think about the number density of the projectile itself. Sorry, I wrote balloon, I meant bullet actually. The number density of the bullet beam actually. Okay, then see, this is the equation that I'm generalizing. Okay, so then I have V bullet times time. Okay, so this is what I've rewritten here. Instead of the number of hits in a balloon, now I'm looking at the number of times, or rather the number of bullets that scatter off. Not all bullets are going to hit the rock. That's exactly what the cross section is trying to measure. Okay, so the number of bullets that do scatter off the rock or the rubber ball is what I'll put in the numerator, and downstairs I'm going to put the number density of the bullet. Okay, it's exactly the same concept. It's as though I have changed frames. Okay, it's now as though the balloons have become the bullets. Okay, I'm now going to the rest frame of the bullet, let's say. This is all equivalent, right? So do we know an example of a real life experiment like this? That's nothing but Rutherford's gold foil experiment. Isn't that right? What did he do? He took a gold foil and focused a beam of alpha particles on it, right? So alpha beam on gold target, right? And not all the alpha particles actually scattered. He counted the number of scatters. I'm giving a very rough picture of what he did, right? But then he knew the properties of the beam that he had, and from that he got the cross section. And this is ultimately how he discovered the presence of a nucleus, right, inside a nucleon, inside an atom. Good? Okay. So the strategy here is again measure and scatter now and get the intrinsic cross section. Okay. Now this combination, right, of the number density of the bullet times the velocity of the bullet, right? So what is that combination basically? That's nothing but the flux, right? That's what we call the flux basically, and it has units of per centimeter squared per second, for example. That's a common unit for the flux. Agreed? So see, just like that we've introduced all these notions from a very simple example. Okay. Now this cross section that we've been writing down, right, it's sometimes called the total cross section. Okay, so what is it a total of, you might ask? Okay, the notion of total comes when you can think of differential cross sections. What do I mean by that? For example, okay, so this must be contrasted with differential cross sections. I can think of the cross section along some solid angle. Okay, in this case, I'm firing bullets, right? Not all bullets are going to go in the same direction. They're going to get scattered in all different directions, right? But they need not scatter isotropically either, actually. All of that completely depends on the intrinsic properties of the system that you're studying. How the beam and the target interact is going to determine this also. Yes, but how will you measure this? Obviously, you're going to measure it by looking at how much scatters, how many scatters you get in different directions, basically, right? So if you were to build a 4 pi detector around the target, you can clearly pick out, most of the beam, most of the scatters happened in one particular direction, almost nothing happened in the backward direction, and things like that. Now, so basically what this is this contains more information on the shape of the object, right? So this tells you about the shape of the target, right? If it was not a ball, if it's some amorphous rock, then it might prefer to scatter bullets off in one particular direction, correct? But more generally, it tells you information about the the scattering potential so there's no need to actually put this in quotes. Oh, so it tells you about the scattering potential created by the source. Remember, in quantum mechanics, when we studied scattering, we had to study, we had to go through scattering potential first, right? And that determined how you solve the Schrodinger equation and get the cross section. That's what we're talking about here. Okay. Again, this is exactly how Rutherford discovered the nucleus. Rutherford's discovery of nucleus. Right? How? Because he saw that, among other things, he saw some of the alpha particles were actually scattering back in the backward direction, which showed that there was something in the middle of the atom that had a very strong Coulomb, that was putting out a very strong Coulomb repulsion. Right? So this is how he was able to assess the scattering potential of the source or the target that he was studying. Right? On top of that, he got some precise relations for the differential cross section with respect to scattering angle. Right? And from that he knew it had to be a Coulomb potential. There was a Coulomb force being created by the object that he was scattering on. Right? So this is how he was able to guess that the nucleus was mostly positively charged and all that. Okay. So, so that's the beauty of these scattering experiments. You can figure out a lot about the unknown target or even the beam by studying these differential cross sections. Okay. So this is not the only differential that you can take. So let's call that 1. You can also look at the differential with respect to some energy. Let's say the recoil energy. That's why I'm writing ER here. Okay. The recoil energy of the target. How would this be useful? So, if you were to plot this versus recoil energy, and then you had a curve like this, let's say. So that clearly tells you that beyond a certain ER max, your particle is not scattering. So that tells you something about their interaction. That tells you something about the target, probably the mass of the target that you are studying, and so on, right? And then the features like these will tell you more about the interaction structure between the target particle and the beam particle. Okay? So taking these differential spectra, angular spectra and energy spectra and whatever spectrum you want to construct, okay, momentum spectrum if you want, invariant mass spectrum, whatever. So taking these differentials gives you a lot more information about the system that you are studying, okay, not just the total cross section. Okay? So this is what particle physicists, experimentalists do all the time. At the end of the day, they are studying all these differential rates, which is secretly differential cross sections, okay, with respect to any observable. Okay, so I'm going to wrap up this class by writing out the differential version of the cross section that we just wrote here. Okay, so instead of sigma differential with respect to something, okay, I'm not going to specify what here, would just be d n scatter divided by, a more generic thing to write would be the number density of the beam times the velocity of the beam, which is what? Just the flux, right? So might as well write it as just the flux times the time it takes for the whole scattering to happen. Okay? This is a lot more general than what we've been doing before. And in the next class, we will see how to use this formula to work out the cross sections for single particle scattering on a single particle. Okay, not a beam now anymore. How do you deal with 2 to 2 scattering? Okay, so we'll derive the cross section for that in the next class. See you then. Thank you.